Hey, aloha, and welcome to Lecture 3 on Simple Linear Regression, or SLR. This is going to be a long one, so grab your coffee or caffeine of choice and sit down and fasten your seatbelts. It's going to be a long and bumpy ride, but hopefully at the end you'll have a good understanding of how to analyze the relationship between two numerical variables. So when we're talking about linear regression, we're talking about a particular technique for modeling the relationship between two numerical variables. So the outline is here, and we're going to pretty much follow that. So let's go to our slides. There's pretty much three parts to this. We're going to talk about how to, what is regression, and then linear regression as a model of the relationship between two variables. And then we're going to discuss the different ways to analyze the results of a regression. And then we're going to talk about how do you tell whether your regression model was valid. That means, is it good for making predictions or forecasts? Of course, at the end of this module, you should be able to do basic simple linear regression, things like describing the relationship between x and y, and determine whether a regression model is significant, and I would add to this, valid. Interpret confidence intervals for the regression coefficients, what those are and what they mean, and talk about interpreting a prediction of y, or the dependent variable, with confidence, checking the assumptions, which is checking the validity of the model, and see if the data contains any unusual values or outliers. So regression is an extremely valuable and useful and common statistical procedure. The word regression kind of means to go back, and you'll see what we're actually doing from the data here is that we're going backwards from the data, regressing, going back into a model. A model is a representation of that data. And when we mean a model in statistics, we mean some sort of mathematical relationship or a formula. So why do we want to do that? Well, when we use regression, it's a way to take advantage of the fact that we have a relationship between two numerical variables, or between an independent and a dependent variable, or at least one of them. And what we want to do is we want to predict the value of the dependent variable from at least one independent variable. We're just going to start out with one independent variable, but you can certainly think about more variables. And the way to think about this is that, well, if I have a relationship between two numerical variables, let's say they're bivariate data, so one varies with the other, and if I can understand how I can observe or control one variable, the independent variable, then I can use that relationship to say, what does that mean, or how does it influence, or what does it mean for the value of the resulting value for the dependent variable, or the thing that it's varying with. So again, it's kind of, given an x, an independent variable, what can I say about something that it's related to, another variable, the dependent variable y. The interesting thing is, of course, as usual, you choose what is independent and what is dependent. That's sort of a meaning relative to the problem itself. From a statistical perspective, they don't really have a whole heck of a lot of meaning. It's just how you work with it. The other thing that we want to do when we do analysis is not just predict values. You don't want to just predict something from an independent variable, predict a dependent from an independent, is we want to understand the impact of changes that an independent variable has on the dependent variable. So that would have to do with like how strong the relationship is. That means that as my independent variable increases, how much does the dependent variable increase or decrease, for example, would be an interesting question on the impact. And we'll talk about those things and how to analyze that. It's a very useful thing to know how strong the relationship is and what is the relationship in terms of the impact one has on the other. So again, the terminology that we tend to focus on here is that the dependent variable is the variable that we want to explain, or that we're going to be the response or the result of something. And the independent variable is the explainer, or the explanatory variable, or the thing that the dependent variable depends on. This will become more clear as we go, and you just need to make a determination of what. So the simple linear regression model, SLR, model again meaning a mathematical relationship, not a complicated one, but just some sort of mathematical relationship that describes how x and y, or the independent and dependent variable, are related. So the simple linear regression model, we'll start with this, has one independent variable, and we always label that by convention x. The dependent variable will be y. Usually we use capital letters x and y, but here we didn't. It doesn't really matter. But again, by convention, the independent variable we label as x, the dependent variable we label as y, and we would say that the relationship between x and y is linear, meaning it's described by a line, the mathematical formula for a line, and that would be our model. So the model is what represents the mathematical relationship between the independent and the dependent variable. We will make an assumption that any changes in the dependent variable y are caused by changes in x. That's why we chose x to be the independent variable. We're saying that x causes changes in y. That may or may not actually be true, but at least logically that's the way we're going to look at it. From a statistical perspective, it doesn't really matter if y causes x or x causes y, because they're both bivariate. They're going to vary together. In other words, if I have a relationship between x and y, if x is related to y in a linear way, then y is related to x in a linear way. It goes both ways. So what kind of regression models are there? Well, regression model again means to take these data points here. Let's just say we have a bunch of sample points. We look at a scatter plot, and we sort of regress them by smushing them down into this line. So we're trying to say, what is the line here, or a linear model, that best represents all these data points? And there's some idea of what best means. So later on you'll see we call that the least squares approach, but there's many other different meanings to best. But in our case, there's some idea that this line sort of best fits this data. And in this case, we look at this scatter plot and we see, it tends to look like a linear relationship, meaning it kind of looks like there's a line. It's just sort of fat, and we sort of smush them down onto this one line that's sort of the average of all of these. And that's a positive linear relationship, meaning that the slope of this line is positive, or it's going uphill. Similarly, we could talk about a negative relationship, negative linear relationship, where it's going downhill. And in the last lecture, we talked about the possibility that there really is no relationship whatsoever. And this doesn't have anything to do with linear or nonlinear or anything like that. It just has to do with that changes in y, or changes in x here, or the independent variable, don't have anything to do with changes in y, or the dependent variable. Here you can see that a change in the independent variable as it increases implies that the dependent variable also increases. Right here, when I increase the independent variable, the dependent variable decreases, hence it's a negative. But this one here, you can see again, as I increase or decrease this, it doesn't matter what I do here, it doesn't say anything about whether it increases or decreases. And one way to look at that is, you imagine that if you look at the best line that sort of fits this here, so the best line that fits this, its slope is 0. It's very important to understand that the slope of this line being 0 means no relationship. It's equivalent to no relationship. It means that changes here don't affect any changes here. They're independent of each other. Whereas here, because the slope is not 0, in fact it's negative, that changes here affect values negatively here, and changes here make positive changes here, affect positive changes there. Of course, there's no reason why we can't have a different kind of relationship. It doesn't always have to be a linear relationship. By looking at the scatter plot here, it seems that a better representation for these points would be to regress to this kind of a curve here. In this case, I think it's like a logarithmic curve, but it doesn't really matter. It's clearly not just a line, because it may be kind of a line up to this point, but then it tapers off very rapidly down there. And so if I fit a line to this, these points would be way far off. So this line seems to fit better in some sense than something like a line here. So the relationship here is probably not linear. But nonetheless, you see that increases here on the independent variable mean increases in the value of the dependent variable. So it's a positive relationship, it's just not a linear relationship. So once again, positive linear relationship means the best thing that seems to fit it is a line. Positive with a positive slope. Negative one is a line with negative slope. No relationship is a line with slope 0. And a relationship that's positive but not linear might be something like this. So the model that we say for a simple linear regression model is given by a formula that looks like this. So this is literally the mathematical relationship between the independent variable x and the dependent variable y. Now it's not as complicated as it looks. We call this the population linear regression model because it talks about that if I had all possible values of data in my model, that this would be the mathematical relationship that would relate x and y given in the population. So what I'm saying is that given an independent variable value x, if I multiply it by a population slope coefficient, it's called beta 1. And again, we use a Greek character to represent that this is a characteristic of a population, not the slope. And just beta 1 just means sort of the first thing. So it's the slope that multiplies the independent variable. And if I add to that the intercept, okay, beta 0, again, a population characteristic, and then I add some sort of random error, then I would be able to get the value for y. So in other words, each value of y in my population is literally equal to beta naught, or beta 0, plus beta 1 times an independent variable plus some random error term. So this represents the relationship between x and y in the population. Now, of course, we don't actually have access to the population in general, so the best we can do is estimate the characteristics of the beta 0 or the intercept, the estimate of the slope or beta 1, and we don't need to estimate this, but we just need to know what the error is, how it's distributed. In other words, it's going to be sort of random error here, and we have to understand how those random errors behave. If we get for example, we just need to know maybe the mean and the standard deviation for this. If it's normally distributed, then we know how errors behave if we know those two things. So again, this is the ideal population model, but in general we won't know what this is or this is, and we don't know what the distribution of that is precisely. But what we can do is estimate this, and the characteristics of the distribution for that. And that's really what our problem is. So when we make a regression, a simple linear regression model, it's going to assume a few things. So we'll assume these things so that we can make estimates of our characteristics. What assumptions we'll make is we're going to assume that the underlying relationship between the x and the y variable is linear. Again, we've seen that the relationship between x and y, the independent and dependent variable, doesn't have to be linear. In fact, there's actually no way in general to tell whether a relationship is linear or nonlinear or this or that. It's just, you can't really tell. It's just a judgment call in some respects. Of course, you can find evidence to strongly imply that it is, but there's no way to prove that one thing it is or it isn't. At least unless you know something about the problem and know that based on the way the problem is set up, that it has to be linear. But typically that's not possible. We also are going to assume that the distribution of the errors has constant variability. So in other words, the errors don't change in terms of variability. For example, if we look at the standard deviation of the errors, it's always just a constant. It doesn't get larger or smaller with different values of x. We'll look at that more carefully later. that the error values are normally distributed. So again, that term right here, we're going to say that this is the error term that represents the random variable, or this is just going to be, some sort of data, that is normally distributed. It's bell-shaped. And they're also going to assume that the values of those errors are independent, that one error at one place is not related to an error at another place. So at least in general, that they're independent of each other. They don't depend on each other, that the value of one is not kind of set or related to the value of another. So graphically, our model looks like this. What we have is, if we look at our scatter plot, where we put x on the, we put the independent variable on the x-axis and the dependent variable on the y-axis, and each point here will be called an observation. So it's a pair of the independent and the dependent variable, or an x and a y. Each one of these is an observation, a pair of x and y's. Then if we have a linear model, then what we mean by regressing is that we're going to find a line that means that it matches our linear regression formula, or our linear regression model, our linear model, which is y equals beta naught plus beta 1x plus epsilon, in this way, that you see that the beta 1 will be this slope. Okay, and the slope, of course, is just like with any line, is the rise divided by the run. So if I look at the rise divided by the run, right, I get the slope of this line. And we're going to call that beta 1. Now that gets the population one. Beta naught is going to be where this line hits the y-intercept. Okay, so it's where the line intercepts the y-axis, so it crosses right there. So the value from 0, from the origin, up to this point here is beta naught. It's where it crosses. Another way of looking at this is where the value where x equals 0. See, this origin here, x is equal to 0. So if x equals 0 and that crosses out, what's left is just beta naught, okay, plus some error. The error, epsilon, this is a random variable, meaning it's just something that varies, is given by the distance between the line and the observation. So we call that the residual. So the difference between the observation and this would be the predicted value, because it's on the line. This is what we think this value, so this value here, for this value of the independent variable, this is what we predict it to be. This is what it actually is. And of course, the independent variable value is the same. The only thing that's different is the dependent variable, and so it was off by this much. That's the error, or the residual. We call that epsilon I for the ith observation. Okay, and all of those epsilon i's are represented by this. In other words, if I look at all the epsilon i's and I look at the distribution of it, then that distribution is represented by this epsilon random variable. Okay, I know it's a lot of terms. Don't get too hung up in it. You'll get used to it as you start working with it. Now that would be ideal for the population, but in general we don't know what the slope, the intercept, and the distribution of the errors are, so the best we could do is estimate it. And so when we estimate what the slope is, we will call that beta B1 instead of beta 1, B1. So we'll come up with some estimate, and the estimate for the intercept would be B0. And you'll see later on that we don't need an estimate for the error. And I'll explain that in a minute. There's no need to get an estimate of the error. What we will get an estimate for of the error is the variability in the errors, but we won't necessarily need to know the value of it. It's actually going to assume to be 0 by the way we do this. So we won't add to anything. So the way we get these estimates, of course, is based on sample data. So we're going to have a bunch of sample observations. In other words, we're going to know some independent variables. This should say xi, by the way, x sub I. This is an error on the slides. That x sub I is going to be some y sub I, some predicted value. In other words, if I have these values xi, I'm going to relate them to values y sub I with estimates beta b0 and b1. So in other words, I get a bunch of observations and somehow I calculate an estimate for the beta 0 and beta 1. I call them b0 and b1, and this is going to be my sample estimate for predicting yi from xi. Okay, so how do we interpret the things that we have estimated? So b0 would be the estimated average value of y when the value of x is equal to 0. So in other words, the intercept is what we expect the on average meaning the mean, value of the dependent variable when the value of x is 0. So in other words, setting x to 0 will give us the estimate for beta 0, which is going to be, we're calling b0, and it's just going to be on average. If we have different, the reason why we say on average is because if we have different observations, then we're going to get different estimate values for this. So what we're going to do is look at what the average of this is, of those for all samples. Similarly, B1 is going to be the estimated change in the average value of y as a result in a 1-unit change of x. This is exactly this definition of the slope. In other words, when I have one increase in the run, or changes in x, okay, then what is the rise that I get, the change in the value of y? And again, if we look at on what is that based on the sample data, we're going to get a bunch of different things, but on average, what is it? We'll call that b1. So how do you find the least squares equation? Now we call it least squares because the way that we do the estimate for the regression, the way we actually come up with the best fit line for the b0 and b1 is we look at the sum of the squares of the errors. So those epsilon i's, we look at the sums of the squares of those. And why we look at the squares is, a bit technical, but basically the squares are always positive, and that's one reason why we look at them. So that you don't, because I could be off either above or below, and they tend to cancel each other out if I took that positive and negative values. So I want always the errors to be positive so that I can add them all up and look at the total error. And so the least squares would say find a b0 and a b1 so that the sum of those squares of the errors is as small as possible. So that's why it's called least squares. It looks for the least sum of the squares values between the error that I get for b0 and b1. In other words, going back to this, if it chooses b0 and b1, so that I get a line so that these, which is the error, so that the sum of the squares, so I take this plus this plus this plus this plus this, all those squared, by the way, is as small as possible. So again, that's just sort of a technical thing. In practice, you just let Excel or Megastat calculate these things for you. It's just important to understand that the best in this sense means the smallest errors in terms of the smallest square of the sum of the errors, or sum of the squares of the errors. They call it some of the SSE, sum of the square errors. You might see that sometimes. There are other regression measures that will be computed as part of computing the regression analysis. If I use Excel, it's just going to give me a couple of things. It's going to give me the estimates for B0 and B1, and it might give me a strength measure called R squared. But if I use Megastat, I'm going to get a much more extensive set of measures that will help me understand how good of an estimate this is, for how good the model is too. Let's take an example. Let's just take our real estate data and say that we wish to look at the relationship between selling price and its size in square foot. Now, the last time we've looked at this, we've seen that it's pretty natural to think that this is bivariate data, that there's going to be a positive relationship between selling price and the size. In other words, the larger the size of the home, the higher the selling price. But it's not going to be a precise, exact relationship. There's other factors that determine the selling price of the home, not just the size, but it's going to be some of it. So in other words, given the size, I should be able to predict at least to some degree of accuracy what the selling price is going to be. So what's controllable or easily managed is the house is the square footage of the house. In other words, given that I know what the square footage of the house, I want to use that to tell me what it says about the dependent selling price. So let's just I take a random sample of 10 houses, and just like with our hypothesis testing and confidence intervals, our observations, it's important that they are assumed to be random, that otherwise we're going to end up with biases and bad estimates. So and then again, it's a random sample is very important. So we have a random sample of square footages and selling prices. Let's say this. So let's just assume that we have these observations of selling prices in houses here, and we want to say what is a prediction for a linear regression model prediction for square feet for house price in terms of number of square feet. So I might go to either use a trend line on trend line on Excel. So let's take a look at that. So I'm bringing up my house price per square feet, and I might simply make just like I did before. I'm going to paste this over here just so I can set my scatter plot. I do an insert chart here, scatter, and now I've got my scatter plot, and now I can just insert a trend line, and if I insert the trend line, I can have it display the equation on the chart here, and you can see that this is going to be the least squares linear regression for this data, and I have the value y equals this slope, that's the B1 x plus 98.248. We'll talk about the r squared in a second, but anyways, this would be the estimate, the least squares estimate for this data. We can also use Megastat. Megastat will give us a bit more detail, and you can see under correlation and regression, we bring up this table here, and we'll select these different options, and we get an output that's something like this. So we would get the predicted house price, again, is 98.24833, which is exactly the same as I had in the trend line equation, plus the intercept estimate of 0.010977. If these values aren't the same, it's simply because I use different data. But in this case, I think they're about the same. I might have a few more digits of precision here. And you'll see that Megastat gives a regression analysis output, and I have a whole bunch of things like this r squared and the r and standard error and an ANOVA table. And this is the important thing, is the regression output, which tells us a little bit about the coefficients and the confidence intervals and things like that. But you can see that we get the equation that with is the estimate. Again, this is not going to be the population intercept. It's going to be the estimate for the population, what we call B0, not beta 0. And this is going to be the estimate for the slope, which is B1, not beta 1. By convention, we call them that. So what's the interpretation of this line? So again, if we look at the scatter plot and we think about the plotting that line, it looks exactly like the trend line. that I got from Excel, because they're both exactly the same thing. So the model really represents the data based on the data. The linear model is only valid for the range of sample data. So the range of sample data that I have, notice that it goes between here and here. This is called the relevant range, meaning that I have observations for independent and dependent variables from here to here and then from here to here. So our model represents that within the relevant range. I could imagine, though, extending this further past the values for the data that I have and also previously to that. If I go outside the relevant range, this is the relevant range, if I go outside of it, that's called forecasting. So I'm actually trying to predict based on data that I don't have any observations. Whereas data, if I look at predictions in the relevant range, that is the just plain old estimation. Again, forecasting is where I try to look at values outside the relevant range, whereas just making predictions would be inside the relevant range. And that's because that if I don't have any data for values out here, it gets a little sketchy in terms of how valid this model is. So the slope being 0.10977, right, square feet, means that is as if I increase the square footage by 1, then the selling price, which is in thousands, increases by 0.10997 dollars. So for every square foot increase, I increase by 0.10977 thousands of dollars. So literally I move the decimal point 1, 2, 3, 10, 100, 1000. Another way of saying it's probably more natural is that for every square foot increase, the selling price will increase by $109.77, or rounded up to $110. So that each square foot of a house is approximately, on average, worth about $110 more. And again, it's a positive relationship because this is a positive slope. It doesn't have a minus sign. It's got a plus sign there. Now, if I have 0 square feet, right, then this disappears. What I'm left with is just this, and that means I'm over here, which is the intercept. So the intercept is going to be 98.248. Now, of course, that's also going to be dollars. So in other words, if I have a house with 0 square feet, right, then the selling price will be 98.248 thousands of dollars. So that would be 98,248 for a house with 0 square feet. Well, that's ridiculous because, of course, a house with 0 square feet is not a house at all. So in this case, we would say that the intercept has no interpretation, because when the square footage is 0, in other words, the x value or independent variable is 0, which is what gives us this, it doesn't make sense to talk about that. That's not in the relevant range. It doesn't. Not only do I not have any data for it, but it also logically makes no sense to have a selling price for a house with no square foot. So in this case, the intercept has no interpretation. It's simply just a way to sort of correct, to make this line fit better and reduce the error. So again, that's summarized by what I just said here. So B0 is the estimated average value of y when x is 0, if x is in the range of the observed x values. But in our case, x equals 0, or 0 square feet, is not. So this just indicates the height of the line, or just an error correction term. Again, reviewing the interpretation of the slope, people tend to have trouble with this, but it's really not as bad as it might first appear, is that if I look at a change in square footage, how does that change house price? And the easiest thing to look at is just 1 square foot increase. So if I increase the square footage by 1, right, then what happens is I look at the difference between this square foot and this square feet plus 1, and what's the change in house price? How does the house price change? In other words, if I go the run up by 1 unit, what is the rise, which is going to be the house price here? And you see in this case that again, it's about $110. And we say on average because it's not the same for every point. It's just on average. That's what I'm going to expect. So this kind of tells us sort of the impact that square footage has on price. You can see that it's sort of each square foot is worth about $110. So some of the properties of least squares regression. There are other kinds of regression, some of which we may talk about in this class, but in terms of least square, which is very common, the regression line will always pass through the mean of the y variable and the mean of the x variable. In other words, right in the middle part for with the average x and the average y, the line will always pass through there. The least squares coefficients are unbiased estimates of beta 0 and beta 1. Unbiased meaning that the difference between the expected difference between the estimate and the actual population one on average is 0. So that might be a little bit of a technical way of looking at it. The idea is that the estimates, it's not sort of skewed up or down. It's just sort of right in the middle. So unbiased estimates mean that when I look at the B0 and B1s, they're not going to be either a little more positive, a little more negative than what we would expect them to be. So that has to do with just the estimates and the interpretations of the slope and the intercept. Now we're going to talk about the coefficient of determination, or r squared, capital R squared. Literally, this is the percentage of variability in the dependent variable that's explained by variability in the y. It's related to correlation. In the fact that if I have a correlation, which you might remember is sort of how does x and y vary with each other, it's the square of that. So correlations can be negative or positive, right? 0 means no correlation, negative means a decreasing relationship, and a positive one means a sort of increasing relationship between the variables. But that's not true with r squared. So r squared being the square of it means it's still a value. It's going to be a value between 0 and 1. And 0, it's going to be a percentage. So 0 means that there is no variability explained by x. And 1, or 100%, would mean that all of the variability in y is explained by x. What we mean by that is that the values of the dependent variable change. They go up and down. So they're not, if it was constant, then we wouldn't have to do regressions. So they change. Those changes, the amount of those changes in the value of y, or the dependent variable, the amount that's explained by the independent variable is r squared. So here's some examples. You'll see I might have a correlation that's negative or a correlation that's positive. Again, squaring them, I get a positive thing, which is the r squared. And if everything is perfectly on the line, right, and this is perfectly negative correlated, this is perfectly positive correlated, then it means that all the variability means, see how these values of y range from here to here? Well, all that variability is explained by changes in x. So in other words, if I change x here, I can exactly predict where y is. If I change this here, I can exactly predict that, etc., etc. So it's 100% in both cases. Of course, that's very rare, if not downright impossible. What happens is that usually not all the variability is explained. So a value between 0 and 1, whether it's a positive or negative correlation, indicates a less than perfect relationship, and means that that percentage of the variability of the y is explained by changes in x. So you can see here that sometimes I have values. Let's take this one and this one. Sometimes for this value x, the value of y is here. Other times the value of x is here. So in other words, for this same value of x, I see two different values of y, right? And so in that case, it's impossible for x to completely explain the value of these 2 points, because the value of x, this value of x can only explain one value of y. It cannot explain both. So what I end up doing is, you can see, I kind of compromise. So the value of y is the value, the predicted line is right here, which is between the two, right? It's sort of the average of them. And so we compromise. So this value of x predicts this value of y, which is neither this nor this. But again, because I can't completely predict where this is or this is with the same value of x, it's not going to have a perfect a strong linear relationship. Another way to look at the r squared is, again, how fat the belt is. So if I look at a line here and a line there that creates sort of a belt, the width of that belt, again, is sort of the strength of this relationship, and that's sort of the r squared. So you see the belt here is very, very thin, so I have a high r squared, or perfect, and the belt here is a lot fatter, so I'm not going to have a better relation. And the fatter that belt is, the less variability is explained by the independent variable, and so the smaller the r squared would be, all the way down to 0. So here's an example of 0. You can see I have no relationship between x and y here. I can tell because the slope is 0. And you can see that anytime this varies, this varies wherever it wants to. So because the variability of here just is completely undetermined by what the variability of this is, no variability of the dependent is explained by the independent. And so r squared is going to be 0. Similarly, the correlation is 0. So in Negastat, you're going to get both the r and r squared. Of course, this is just the square of that. Unusually, because it's between 0 and 1, you see that squaring something between 0 and 1 actually makes the number smaller. So the way we interpret the r squared, say we have 0.581, is we'd say something like, well, 58.08% of the variation in house prices explained by variation in square foot. But of course, this says 581, but this is 0.5808, but it's just rounded up here. So you could also do that. You could say that 58.1% of the variability in house prices explained by variation in square feet. Correlation of 0.6762 says it's a fairly strong positive relationship, or direct relationship, because the closer to 1 we have, the stronger the relationship. The standard error is basically the standard deviation of the residuals. The residuals meaning the errors, those epsilon i's, remember that? So if you look at these, take all those epsilon i's and you look at the standard deviation, you pretty much, the sample standard deviation, you get the standard error. The standard error is interpreted as the typical error in the units of the dependent variable of the estimate. So typically when I make an estimate of housing prices from square feet, I'm going to be off by $41.33 thousand, or I'm going to be off by about $41,330. So in other words, on average, my predictions are going to be too high or too small by 41,330. Okay, so that's what we need to say about interpreting the strength characteristics and the slopes and the intercepts and what the model is for linear regression. How do we know that the model is any good? How do we know that our relationship actually holds? Well, we can resort to hypothesis testing for that. And the way that we do that is we can say, is there a linear relationship between x and y? Well, what we can do is test the hypothesis, right, that the population slope is either equal to 0 or not equal to 0. So remember that if the slope was actually equal to 0, if the population slope is actually equal to 0, there is no relationship. Not just no relationship, no linear relationship, because this was based on the linear model prediction of it. If we can have evidence to support the hypothesis that beta 1 is not equal to 0, in other words, the unknown population slope is not equal to 0, then we would say that there is a relationship. Now, the way we do this is just the same thing. We're going to use a t-test, and the way we're going to use a t-test is because our errors are going to be assumed to be normally distributed, and because they're normally distributed, we can apply the t-test to figuring out whether what the unknown population slope is. And we just take that data and we run it through an ANOVA. So an ANOVA will give us a test for the population slope, and to get the p-value just like we do. And if the p is low, then there is evidence to reject the null in favor of this. If the p is not low, that means there isn't evidence. So we can only get evidence that there is a linear relationship, not that there isn't. So here's an example of our housing prices again. How do we know if square footage of this house actually affects its sale price? In other words, how do we know that that housing price is dependent on, or has a linear relationship to, or in other words, affects housing price, sales price? So that's a question of asking. This is just the estimate for the slope based on the sample data. We just want to know if the population slope for housing prices and square footages is not equal to 0. So we get our regression output, and you'll see that our regression output will give us a table that says intercept and square feet. These are the coefficients. These are just these values here. And this is the error, the standard error in what these are based on the estimate. The t-statistic is to tell us what value we expect to be in our confidence interval or not. But most importantly, the same thing is just to look at the p-value. And we see the p-value of 0.01039. Well, just like any p-value, we just want to see, is it less than our required level of significance? So if we're testing, if we say we require at least 95% confidence, then we would check to see if this is less than 0.05. And in fact, it is less than 0.05. The actual confidence we have is 1 minus this p-value. So 1 minus 0.01039 is about 98.96. So we can be 98.96% confident that square foot is related. In other words, we reject this. There is evidence to reject this in favor of this because this p-value is less than the required level of significance, say 0.05. And we actually are fairly confident. And how confident? Well, 1 minus the p-value of that. Again, the reason why we reject it is because we've chosen some required level of significance like 0.05. If we chose a required level of significance, say 0.9, say we want 0.001, then we would not reject. But that would be wanting like 99.9% confidence, which is probably too high. Okay, so that's looking at the confidence in that there is a relationship. And by the way, when the p-value for the slope, which is here for square feet, because this is the coefficient that's in front of, right, the dependent variable, if that p-value is within the less than the required level of significance, then we say that it is significant, and we say that this square footage is a predictor, or a significant predictor, or something that has a significant effect on house price. Once we know that the slope is in the population is likely to be non-zero, we don't really actually know what that slope is. All we know is that we strongly believe that it's not equal to 0. So this is just an estimate based on the sample data. But of course, if we took another random sample, we'd get a different estimate for this slope. If we can still understand how accurate this is by getting a confidence interval, just like we did before. So this is sort of an average. And so how good is that sample average as an estimate for the average in the population, or the mean population? That's given by this lower and upper boxes here. So you can see that the lower end of the confidence interval for this slope is 0.03374, and the upper end is 0.18580. In other words, with 95% confidence, the actual population slope for square footage is going to be between this and this. So you notice that this value is right in the middle. 0.1097 happens to be right between those two. The way we interpret this is we say with 95% confidence, meaning because it's a 95% confidence interval, 95% confidence, or at least 95% confidence, that as the square footage increases by 1 square foot, the housing prices will increase between $33.74 and $185.80. So another way, you can also say this like this. You can say that housing price increases between this and this for every 1 square foot increase. Because the interpretation of the slope, remember, is that for an increase in the run, what is the change in rise? Okay, in other words, for an increase of 1 unit in the independent variable, what is the increase or decrease in dependent variable? Now, by the way, you should take a look at this, that this confidence interval here is not related to this p-value exactly. So in other words, you wouldn't say that I'm actually 1 minus this p-value confident that this is true. This confidence interval only gives us a 95% confidence interval. There's no such thing as the actual confidence. That's only for when we test a hypothesis. Another thing we might want to do is not just look at what the actual population slope is, but we might want to know that given a predicted value, which is going to be something on this line, well, how accurate is that? How confident are we that it's within a certain range? So when we look at the estimate or the predicted value, and then we give it a range with confidence, we call that a prediction interval. Now the prediction interval is for an individual y given an x. So in other words, let's just say I'm trying to predict a certain value for an independent variable x sub p. So x sub p meaning for the predicted value. So what I'm going to do is that's going to be the predicted value. But if I want to know with confidence, I'm going to end up getting a range between here and here. And so I can say with 95% confidence, the predicted value of y given this value of x is going to be between here and here. So that tells us again how good our prediction is. You'll notice that this funny curve like this. And what happens is that, remember how we said that in a linear regression, that linear regression always goes through the mean value of the independent variable, that's right here, and the mean value of the dependent variable here. So this point here is actually the mean x and the mean y. And so all the predictions that go outside of the average x and the average y, right, this is going to be the confidence interval, right, for the mean y, and this is the confidence interval of the mean y. Well, as I move away, okay, from the mean, my confidence interval is going to get larger because I am going to be less and less sure that of what my predicted value is, because I'm moving away from the mean. The mean is sort of the best estimate for a particular value of y of that data. But as I use less and less of that data, my confidence interval is going to get bigger. So another way of looking is that as I move away from the mean, I'm actually using less sample data. Less sample data means I'm going to have a larger confidence interval. And it looks like this. It tends to have this sort of shape. So you can see that as I move farther and farther away, it goes way up. So the farther away I get from the mean, the less accurate my prediction is. Okay, let's take a look at this. Let's just say I want to predict the house prices for 2,000 square feet. So you notice that 2,000 is not one of my sample points here for square foot. So what I'm going to do is I'm going to take 2,000 and I'm going to, see that's square foot, I'm going to multiply it by this slope, and then I'm going to add it to the intercept, and that's going to be my estimate. Then what I want to know is how good is that? So I put that in here and I calculate that it's 317.85. So the predicted price, selling price for a house with 2,000 square feet, right, this is 317.85 thousand, so 317,850. So again, this is the predicted value given that independent variable value. So how good is that? Well, how good is it? It'd be based on the prediction interval. So again, by using Megastat, you'll see that I can get a predicted value for y. So if I put in 2,000 square feet, it tells me that's what the predicted value is. And I get two confidence intervals. I get this confidence interval here, and I get the prediction interval. Now the confidence interval means that on average, if I keep estimating with different samples, right, my predicted value is going to go between 280 and 355,000. Now, that's not that interesting. What I want to know is what is the predicted value for this given prediction. In other words, for this particular 2,000, for this particular model, then you'll see that I use the prediction interval, not this interval here, because this would be on average with lots of different samples. Given the samples that I have, the prediction for this particular value is going to be between 216 and 420,000. You'll notice that this prediction interval is larger than this prediction interval. Again, this is just going to be based on the averages, and this is still going to be for a particular value. So the way we write that again is that the prediction interval is between, we can be 95% confident that the home price value is going to be between 215,503 and 420,605 for a 2,000 square foot home. Okay, so I hope you're having fun so far. I know this is a lot of stuff, but feel free to pause and take a break and come back to this later if you need to. It's very important that you look at and take notes and try to really understand what's going on here, and write down questions that you have or examples you'd like to see. Again, once you start working with this, it becomes a little more clear. So in the abstract, it seems to be a lot of stuff. Okay, so now what we want to do is, now that we understand how to check, how to get an estimate for our simple linear regression model, and that means just understanding an estimate for the slope and for the intercept, and that we can test whether there is a relationship or not, a significant relationship, by looking to see whether the slope is 0 or not 0. And that we know how good that relationship is in some respects by looking at the r squared and the r, but the r squared meaning how much variability in the dependent is explained by the independent variable. And we also can get estimates for what the population slope is and what the prediction is with confidence, so how accurate are those. Now, all that stuff is based on assumptions. All those estimates and all those error analysis and all that confidence stuff is based on a bunch of assumptions. The assumptions for the simple linear regression model are very important to be able to get accurate p-values, for example, in terms of whether the slope is 0 or not 0, or an accurate confidence interval for the slope, or an accurate prediction interval. or accurate and meaningful, I should say. So once again, our predictions and our conclusions that we come about the model that we use, the simple linear regression model, are based on the assumptions that are made for this, and they are, of course, only as good as the assumptions are valid. So when we use simple linear regression, or actually anything, it's very, very important to check the validity of the assumptions that it's based on. Just like with the hypothesis testing, we had to check, say, that the data was normally distributed, or for confidence interval that it was normally distributed. If we're going to do a a t-test, for example, we also have to check a variety of different assumptions for our regression to make sure that everything is good. Now, fortunately, even though there's a few of these things, it's a little more complicated than the hypothesis testing case. Even though there are a bunch of assumptions that we need to check, practice is really not that difficult. It's not a whole big deal, and it's usually you don't have to be that fussy about it, but you do need to check. So we're going to look at a residual analysis. Now, a residual, of course, is another word for error, or again, those epsilon i's, the difference between the predicted and the observed. So a residual analysis means we're going to kind of analyze the errors to try to understand how good our assumptions are. So we need to check these four assumptions: the linearity assumption, constant variability, and the normal residuals assumptions, and a check for independence over time. Now, there is a handout on this that will explain what you need to do if you forget. I'm going to bring that up for you right now so you can take a look. So you'll see that we have the checking assumptions and regressions rule of thumb here, and you can see that there are checking for linearity, constant variability, normality, and independence. So even though I'm going to go over some of the details now, this is kind of a quick reference for that. By the way, there's a reference for using Megastat also, sort of a guide to the Megastat regression analysis. And also, there's another couple thing, regression questions and outliers and opportunities, which we'll get to in a minute. Okay, going back to our thing. One of the things that you want to do is that when it comes to checking the validity of assumptions, oftentimes a picture is worth 1,000 words. So often graphing things will really help you quickly determine whether there's any issues with your assumptions. So we're going to be able to do a graphical analysis of our residuals. One of the things we're going to look at is plotting the residuals, where the errors versus x and versus the predicted y, and what does that tell us. Creating a normal probability plot of the residuals to check for normality, or we can use the skewness or kurtosis rule of thumb. But of course, if this fails, then we might go to that, and to look at the Durbin-Watson statistic to look for independence over time. Okay, so let's talk about looking at residuals as an analysis for the linearity assumption. So linearity assumption is that our model for that we are using is in fact a linear model. In other words, that x is related to y according to the formula y equals the intercept plus the slope times the independent variable. So how do we know that? Well, one quick check of that is to do a scatter plot check. And if we look at a scatter plot check, you can see, well, this does not look linear. You can see it has a sort of a rainbow, whereas this one has a linear look. And another way to look at that maybe more easily is to take the residuals. Instead of looking at the scatter plot, look at the residuals, which is the difference between the actual and the predicted. So in other words, it's all these distances here, right? All those little distances there. And plot that versus the independent variable. And you'll clearly, again, see a rainbow. And that would tell you that it's not. If you're concerned about it, there are some rules of thumb that by adding a trend line to this and things like that, and you can see whether or not there tends to be a slope that's 0 or not 0. What you do want is a slope of 0. So here, it seems pretty linear, but plotting these very same things, and now they're just taking this line and kind of moving it down there. But in other words, I'm plotting all these distances over x. Again, you'll see that if you look at this, there is no relationship between x and y and the residuals here. In other words, the slope is 0. That's good. That means that the assumption of linearity holds. So here, if there does seem to be a relationship, then there is, or any pattern. If you see any pattern at all, then it's not linear. If you see no pattern like this, then no pattern meaning that you can see that as I change x, it doesn't seem to do anything to the errors or the residuals, then assumption of linearity holds. So another assumption that is made is the constant variability assumption. And what's constantly varying is the errors. Again, the residuals need to be constantly varying. So a constantly variable, if I look at my errors here, you can see that if I look at the standard deviation of all these things, it doesn't change now this is looking at the predicted value of y. So the predicted value of y here, you can see that as the predicted value of y changes, goes higher and lower, the error is still varying at the same rate. But looking over here, you can see that the predicted value of y, as I increase the predicted value of y, as the predicted value of y increases, you can see that the variability increases. In other words, the range is larger here for larger values of the predicted versus smaller. Similarly, you can look at the scatter plot, and you see on a scatter plot, you kind of see this wedge or cone here, sort of a bullhorn. And here you don't see it. It sort of varies normally. Here again, you see sort of a wedge shape. And if you saw the wedge shape going the other way, that also would be non-constant variance. It doesn't matter whether it's increasing or decreasing variability. What you want is constant. Another way to look at that is you kind of think of this as a control chart. If you think of this as a control chart here, you can see that this seems to be out of control because the ranges are getting larger and larger and larger, whereas here this is in control. Okay. Another assumption that we need to make is the assumption of normality of the residuals, or normality of error. So remember that epsilon, that random variable for the error? Well, we made the assumption that it is normally distributed. And that is because if we make that assumption, then we can calculate things like p-values for the slopes and stuff like that, and they'll be accurate. Well, this is pretty straightforward. Just like anything that if we have a bunch of data, we can check for normality by looking at the skewness and kurtosis. Is it between both -1 and 1? Or if that doesn't turn out very well, maybe there's a couple of points that are sort of outliers, we can look at a normal probability plot and see whether it looks like it's on a line. And if that's the case, we'd say that the assumption of normality holds. And again, what we're looking at the normality of is the errors, or the residuals, which is the actuals minus the predicted. Okay, so we just treat it like a data set and see whether it's normally distributed or not. And the final assumption that we make is the assumption of independence. Now, it turns out that the assumption of independence is only needed if the data is collected over time. In other words, if I have time series data, so if I'm looking at, say, revenue over quarters, then I would need to look for the assumption of independence. If I have randomly sampled data, in other words, it's not collected over time, it's totally randomly sampled, then I don't have to worry about the assumption of independence. But if I do have time series data, I need to check the assumption of independence because things that are collected over time tend to be related to each other. In other words, the changes from one time period to the next tend not to be as great as if I look at random samples. And simply because that usually a process is occurring over time, and so things don't tend to bounce around as much when they are near to each other. So one easy way to look at that is to look at the Durbin-Watson statistic, and the rule of thumb is if the Durbin-Watson statistic is greater than 1.3, then the residuals are acceptably independent. There's also a graphical way of looking at this, but the Durbin-Watson is pretty reasonable way to do it. And the graphical one is if you graph the residuals versus the independent variable, then if you see sort of a snaky pattern, then that would not be independent. Okay, so again, let's take a quick look at our charts here. So checking assumptions and rule of thumb, we have this lovely guide here that says, one, when we have a regression, linear regression, we need to first check to see whether there is linearity. And you could look at the residuals as the independent variable and see that there is no pattern or that the slope is 0. And there's a rule of thumb for that. You can also see that checking for constant variability, you can plot the residuals against the predicted values. Okay, this is a little mistake here. That's not supposed to be x. That's supposed to be predicted. But you can see that if it's versus the predicted values here, you see sort of a wedge shape either direction, that they don't have constant variability. Checking for normality, just look at the residuals and use your usual normality tests. There's some rules of thumb here that can help you. And checking for independence, you can plot the residuals over time, over time, and see if you see a snaky pattern. Or use the Durbin-Watson statistic and see if it's greater than 1.3. So if it's less than 1.3, bad, over 1.3, okay. These also give you some ideas like if they are bad, if the assumptions are invalid, is there something you can do? And that's a topic we'll take up a little later. Okay, so moving on. When you have a regression, it's not uncommon to have a couple of unusual data points. So those unusual data points sometimes can throw off your predictions. It could be that the way that you sampled the data was in a certain group and then you sampled something at another time that was in another group. It could be that there's a true outlier or maybe just an error in collecting your data. The other thing you want to do is maybe also look at what points tend to influence the most in terms of what predicts the dependent variable. So how do we do that? Well, we can look for outliers from the predicted values by using these studentized and studentized deleted residuals. So Megastat will do this for you. So let's take a look at this. So looking at Megastat, so remember we made our little scatter plot. We also, if we use the Megastat's regression analysis, it's going to give us this plus the output here. And you can see we have our ANOVA table, which gives us our p-value, and a p-value for the square footage, which is that the square foot is a significant predictor because its p-value is small. Now you can see here that notice we have a Durbin-Watson also. So we have a Durbin-Watson of 3.22. But since this data is not time series data, we don't have to worry about that. So it's not surprising that I get a high Durbin-Watson greater than 1.3. But in terms of unusual data points or influencers, you can see that Megastat put these in blue because it says that the leverage is a little too high, a little more than twice. So that in terms of square feet, that the value is more than twice the average value. So the average value of 0.2 is what we normally get, but we get something that's more than twice that. So that's unusual. It seems to have an undue influence on this. So that's a high influencer. And looking at Cook's D identifies that we have one influential observation here. Again, it's not surprising that it's related to the high leverage value. So usually you want values to be larger than 1 if I'm worried about this. So this is unusual but not ridiculous. And you see most of these values are pretty small. So Cook's D along with the leverage tell you about unusual distance. Let's take a look at that. What is observation 8? So going over to here, we've got 1, 2, 3, 4, 5, 6. Let's see if we can find it. 7. See, 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's this point right here. Another way to do that is observation 8 is going to be from our data, right? 1, 2, 3, 4, 5, 6, 7, 8. So it's the point 224.50 square feet and $324,000. So 2450. Again, looking at that, let's see if that's it. No, I guess I got it wrong. There's 2450. So that looks like it's the high leverage point right there. Okay, now, it's not always true that you count them in order and that's where they're going to be. That would only be for time series data. So I made a mistake on that. I apologize. I'm sure you caught that. This is the 0.8. And again, I found that because it's in the order of the data, and I just looked at what those two values were and then looked it up on the scatter plot. So this one. Wouldn't be surprised if this is the other unusual point. So this is 2350 and 405. 2350 and 405. So that's observation 7. And going to Megastat, you'll see that observation 7 also has a fairly high Cook's distance. This one also has a high Cook's distance, but these ones are really ridiculously high. Not ridiculous. It's only over 1 that we'd really worry about. So in this case, we don't really have anything terribly unusual. Okay, going back to our values. Let's see. What kinds of outlier issues might occur? So there's a variety of different situations for which you might see extreme points that may or may not be unusual. So here we see this point here is an extreme in both x and the y, both the independent and dependent variable as an observation. Now it could be, you can see it does fall in line with the pattern here, so it's not going to affect the prediction very much. And it might actually, in fact, not be an unusual point at all. It could simply be that, well, as I was collecting this data, that it was just unexpected that I just collected some data outside of that range. And now right here at B, we have a value that's both extreme in x and y that does not fit the pattern. And this one will likely affect the prediction, and it would have a high leverage value. So it'll strongly, it's going to pull this line up higher. So the slope, instead of being like this, is going to be more like that. Okay, this one the slope wouldn't change, but this one the slope would change to head towards that one. And so it's going to have an undue influence, and it's likely an outlier, being an unusual point, because it doesn't fit the pattern. So you want to investigate why. Is that really a valid point? This is extreme for x and pretty much typical for the y value. In other words, you see the average y is right here and the average x is here, and you can see it's pretty much right there in the middle. So it's definitely within the range of the dependent variable, but it's outside the range of the independent variable. And so more that it's away from the regression line here, the more it's going to influence. It's not going to really influence the dependent variable so much. But you can see, again, it's going to pull this line away. So this is also ought to be investigated. You ought to investigate whether your independent variable value observation is correct or reasonable. But this is one that's extreme in the y. It's outside the y range, see, but well within the x range, and so it's going to affect the regression, but depending on how far away it is from outside the y range. And again, this one you would investigate whether the observed dependent variable is in error or not. Now, this one's an extreme in the pattern, but not in x and y. In other words, it's both in the range of x and the y, and it's not going to change the slope of the line. See, it's on the slope, but what will change is the intercept. So instead of crossing here, it's going to draw the thing and make it cross up here. So the question is, do you include these points or not? Well, again, what you want to do is, if you see points that are like this and extreme, understand how they are extreme, and then you want to go and investigate the source to see how reasonable they are. It's not a wise idea to just arbitrarily throw out data. Okay, you should throw out data when you have some reason to believe that that data is an outlier or an unexpected or unusual or an error point. Otherwise, you need to further investigate why you're getting points like that. Okay, so that's that. That's what we have. It's a lot of stuff, I know. We talked about simple linear regression and how it's analyzed. We look at how those coefficients of slope and intercept are calculated. And we looked at the measures of strength in terms of correlation and its square, which is r squared, which is the amount of variability, and SE, this is the standard error, which is sort of on average how far off will our predictions be. So don't forget that there's a variety of other resources for you to look at. Let's just take a quick look at that. So other than the checking assumptions in regression, there's the Megastat, how to use Megastat regression analysis. There's a basic questions and answers. So when you are doing a regression, you might want to know, like, when do you use regression? How do you get the best straight line? So there's things that can be asked, are answered in this 9 questions and answered. So you probably want to take a look at that. And there's this whole section on detecting outlying and influential observations using Megastat. So I know I only went over it very briefly, but you should take a quick look at some of this stuff to help you understand how to use Cook's distance and leverage to identify potentially unusual or unexpected points. Okay, I hope that you're awake, and I'll see you